Hello there, and welcome to my tutorial on how to model a full-wave diode rectifier in LTspice. This will require a few simple calculations, which I like to do in Python. You can use MATLAB, or just use pen and paper. But I find Python to be a powerful and free tool for engineers. I've been using it for my homework for years, on the same laptop that I'm using to make this video. A laptop whose charger has this big brick in the middle. One day I wondered what it was for. Turns out that there's a rectifier inside. Wall current is AC, which means the voltage alternates between positive and negative, and the current flow alternates between two directions. However, batteries need DC. Diodes only allow current to flow when the voltage is positive. The bridge configuration from my circuit diagram only lets current flow through the load in one direction. The top graph is the AC input, the one below is the DC output. In this tutorial, you will learn how a bridge rectifier works, and how to design one in LTspice. To keep things simple, we will be modeling a resistive load. No inductive loads, no freewheeling diodes. Keeps things relatively simple. According to the specs on my charger, the average DC voltage output is 20 volts, and the maximum current is 8.5 amps. In my version of LTspice, I've estimated the voltage drop across the diode to be about 0.9 volts. Trust me, that number will be important later. Find what it is on your LTspice and write it down. The other super important variable is the magnitude of the input AC voltage waveform. You can calculate that from the output voltage. Vm equals VO times pi over 2. You can rewind to my notes and sketches if you're unsure where that comes from. But you can't forget to take into account the voltage drops across each diode. Remember, I said that only two diodes are conducting at any one time, which means you have two voltage drops between the input and the output. The LTspice model will require a resistance where the current won't exceed the rated maximum current. This can be calculated with Ohm's law, V equals IR, but in real engineering design, it's a good rule of thumb to add an extra 25% buffer to the resistance. Hence the expression 1.25 times V out over I out. Click the green play button in the upper left portion of the screen to calculate all of these values. In order to display them, simply enter a variable name in the console to the right and press enter. Using this method, we can determine that the magnitude of the voltage is about 33.2 volts, and the resistor should be set to about 2.94 ohms. And now we move to LTspice, the circuit designer's best friend. The first thing to do is lay down all your components. Hit F2 and type voltage into the search bar. Double-click to lay down the component. Right-click where it says V1 and you can rename it to whatever you want. I like to call it VS for source voltage. Right-click on the symbol to enter the parameters and copy the magnitude from the Python script. Your frequency will be 60 Hz in the United States, and for this simulation, I find it works best to have 3 wave cycles. Next, choose a diode from the taskbar above. Hit Ctrl-R to rotate it 90 degrees until it's facing upward. Place 4 of them in a rectangle. That way they could be connected in the bridge formation. Last but not least, we have to add the resistive load to the circuit. Simply select a resistor from the same taskbar in which you found the diode. Next, change its value to what we calculated earlier, a little over 2.94 ohms. And, because there's only one resistor in this circuit, I like to change it from R1 to simply R. Now, for the complicated part, connecting everything. First, click on the wire button and connect to components that way. Unfortunately, this task does take a while, so I'm just going to skip to the end. Feel free to pause the video while you compare your work to mine. Click the button that looks like a running man to run the simulation, but first it will prompt you for parameters. Choose a transient analysis. Set it to start immediately, and make the time step small. I usually choose 1 microsecond, but it takes longer to simulate smaller time steps. 50 milliseconds is usually a good place to stop, since that's exactly 3 wave cycles. The speed and mileage of your processor may vary. If you hover the cursor just above the resistor, you'll notice that it turns into a voltage probe. Click and it will show you a waveform. This is the DC output voltage as a function of time, specifically from the 0 to 50 millisecond range that I inputted. You'll notice that this DC waveform is never negative. It's a repeating waveform which oscillates between 0 and a positive peak. Now, you may notice that the peak is well above 20 volts, but I assure you, the average is near 20. Don't believe me? Just hover your mouse right over that green text that says VN006, Control-click, and it will show you, among other things, that the average DC voltage output is about 20 volts. Now that we've modeled a full-wave diode rectifier with a resistive load, what would you like to see next? A resistive and inductive load? Perhaps a freewheeling diode or capacitor filter? Leave any suggestions in the comments below, and don't forget to like and subscribe.